Okay, today very similar to last day's lesson, except what we're looking at for our goal is we're talking about quadratic models. So we're going to be able to identify a quadratic model and then use those characteristics to talk about different quadratic models. So on with the notes. So just like when we talked about linear, we can tell whether something is quadratic from its table of values. Now, what we know about quadratics is that their second differences are equal. So it means we have to do a little bit more work in order to determine that. So what I've done this time is we have our table of values and I have a first differences column and a second differences column. So I have this table of values I know is a quadratic model. So when we're looking at this one, again, what we're doing is we have to then actually do the subtracting. So I'm going to bring up the green for the first differences. And so I have to start with 142 and I need to subtract 202. Okay, now I'm not, obviously I don't have room for all my numbers in here. So as long as you realize that that's what we're doing in between here is we're subtracting. So we end up with negative 60 here. If we take the next one, 202, subtract 238, again, we have a negative number. However, this time it's negative 36. And our last two numbers that we're going to subtract, 238 from 250, and we end up with negative 12. I think I said that opposite, 238 take away 250. So first difference, as you can see, we have negative 12, negative 36, and negative 60. Obviously, those numbers aren't the same number, so therefore it is not linear. So now what I do in the second column is I literally go and I take negative 60 and I subtract a negative 30. Really watch out with the negative signs here. So negative 60 is really going to be plus 36. And when I do that, I end up with 24. The same is going to happen here, negative 36 minus a negative 12. So we're going to have negative 36 plus 12, and that equals 24. Now, I didn't make the table of values as large this time. I would have preferred to have a few more numbers in my second differences in order to make a better um, a sorry, a better indication that for sure that this second differences are equal. So when I do that, you can see that they are the same. Okay, so they are the same. So you have to do first and second differences in order to prove that they're the same. Now, when we look at the other way I can tell if something is quadratic has to do from an equation. And maybe what we'll do before we move on there, so I keep changing my mind, is we'll maybe make a statement about this so that if you go back in your notes. So because these are the same, therefore quadratic. And you can tell I'm out of practice using my little writing pen. So we know it's quadratic because those numbers there, the 24, are the same. All right, sorry about that. Okay, let's go on very quickly from an equation. Now, an equation of a quadratic, a couple different things we have to consider. It has to be an equation that can be written in the form y equals ax squared plus bx plus c. Sometimes it doesn't look like that, but it says can be written. So if you could rearrange it so it was in this form, then it's quadratic. So the main thing you have to really watch out for is the independent variable is to the power of 2. Now, if I look at an equation like this, the independent variable is an x. Okay, so that's what it usually is when we're graphing on the Cartesian plane. However, the reason I use the independent variable instead of the x is to the power of 2 is because there are times when we're not using x's and y's because we're in a word type question. So remember we saw this in the linear, we had a y squared equals, 3x or whatever. This would not be quadratic because the y is dependent on the x. Therefore, this is not a quadratic. So it has to be the x, the independent variable that is squared. So let's look at a couple of, well, more than a couple examples. So out of these, which ones are quadratic? Well, when I look at this one, I have y equals, so y's to the power of 1. Then I have 2 bracket x minus 3, all of that squared. So what does that mean? Well, you know from exponents that really what's happening here from FOIL that this really creates an x squared in here. So I could FOIL this, and if I simplified it, I would end up with an equation very similar to this y equals ax squared plus bx. So this one is a quadratic. The next one, y's to the power of 1, x is to the power of 1, so it's not. The next one, I have an x here and a y here. You can see this is to the power of 1. Well, this x is kind of to the power of 1, but it's kind of in the wrong spot. It is an exponent. So, and that exponent is not x squared. So therefore, this one also is not a quadratic. And the final example is y equals 2x squared minus 3. We have y to the power of 1 and x is to the power of 2. So therefore, this one also. So there's two equations here that are quadratic. And the last thing that we can say about quadratics has to do from their graph. Now we know from their graph a couple different things. We know that it's the shape of a parabola. And parabolas come in two different forms. One form is a U turned upside down, or it could be a U turned upward. Okay, so that is the typical shape of a parabola, and that tells us it's quadratic. Now, when we're comparing quadratic models, so when we're comparing one from another, a few different things we're going to look at or that we can comment about. First of all, we can comment about its direction. Does it open up or down? Obviously, if it opens up like this, what we end up having is the vertex here is important. It tells me there's a minimum value, so I'm never going to go below that. So this becomes minimum, and if I have a parabola that opens down at this location here, again where the vertex is, it is a maximum value. And I'm just going to type those in really quickly rather than print them because I do a better job of typing. So this one creates the minimum, and this one here is a maximum. And notice that happens at the vertex. So we can, when we're comparing quadratic models with one another, we can talk about whether they have a minimum value, a maximum value, where that's located. The other thing we can talk about is its vertical intercept. And what that means is the y-intercept again, the same way as we talked when it was linear. And also when we're talking about quadratic models, it's the initial or the starting value. It's what's happening if we're looking at something that talks about time. It's the starting time. The other thing we can talk about also when we're comparing has to do with the stretch or shrink. In other words, the steepness of the graph. Now, when we're talking about the steepness of the graph, it's like a rate of change, but remember when we're talking about parabolas, the rate of change changes at different locations. Okay, so it has, infinite slopes. But one thing we can say is that it changes direction at some point. So for instance, if I was reading this graph here from here to here, for instance, this graph is going down. So the rate of change is decreasing infinitely. And going this way, it's increasing infinitely. Okay, so that's one thing to keep in mind as well. So summary of our quadratic models. The table of values, the second differences are equal or constant. The graph is a parabola. The equation can be written in the form y equals ax squared plus bx plus c. And the rate of change changes and changes direction throughout. Okay, so it changes at the vertex. Also, the vertical intercept is the initial value, the starting value. Okay, it's time for you to do some practicing.